Okay, so I'm going to go over the warm-up from November 5th, and in case you have questions or you didn't get a chance to stay to watch me go over the answers. So this is Chapter 9 material. Again, your quiz will be on Chapter 9 and 10 material. The first question gave you the following limiting fashion reaction. Because it's limiting fashion, in the first part of the problem, I'm asking you for the theoretical yield. So your first step should be to find the limiting reactant. The reactant that will tell you exactly how much of the products are going to be made. It controls the amount of product made. So, to find the limiting reactant, you need to first you're converting each reactant from, in this case I'm giving you grams. I could be giving you moles, but here I'm giving you grams. You need to be grams to moles of product. It's your first step. So if I start with the 10 grams of zinc, 10.0 grams, I need to write this out so I know it's zinc sulfide grams. Keep track of those units. To convert from grams to moles, which is allowed, and as always on Chapter 9 lecture notes, if you refer to page 4, I believe it is, there's that little map I give you where you can convert from atoms to moles, moles to grams, but never ever from atoms straight to grams. So refer back to that when you're doing these problems. So I can go from grams to moles by using the molar mass of zinc sulfide. If I calculate the molar mass of zinc sulfide using the periodic table, I get 97.46. As always, follow the sig figs according to the periodic table you are using. Grams have to go on the bottom of zinc sulfide because I want them to cancel. And moles are going to go on the top because I want to end up with moles. Make sure I set this up correctly. The grams cancel. The number always stays with the grams in the molar mass. Now I have moles of the reactant. To find moles of product, the thing that relates moles of something to moles of something else is your balanced chemical equation. So in the chemical equation that is balanced above, I see I have 2 moles of zinc. That's going to go on the bottom because I want it to cancel, and I want to be left with moles of zinc oxide because that's the product I'm asking you about. And then according to the balanced chemical equation, 2 moles of zinc oxide are produced if I use 2 moles of zinc sulfide. Make sure my units are canceling and I've set them up correctly. I'm left with moles of product, so now I can actually calculate this. And I get the lowest number of sig figs because I'm multiplying is 3. So I need to report 3 sig figs. 1, 2, 3 sig figs. Moles of zinc oxide product. I'm going to do this again for the other reactant to see how much is made. If I start with 10 grams of the given oxygen, now I multiply by the molar mass of oxygen, which I calculated to be 31.98988 grams of O2. Moles on the top. Grams cancel, I'm left with moles. Now to get from moles of O2 to moles of zinc oxide, I use the balanced a chemical equation. For every 3 moles of O2 used, I get 2 moles of zinc oxide. Make sure my units cancel. Those are opposite each other, so they cancel. I'm left with moles of zinc oxide. If I do the math, again, lowest sig figs is from the 10.0, so it should be 3 sig figs. If I compare these, I notice this number is lower, so the limiting reactant is zinc sulfide. Again, the limiting reactant, not the product. So I need to use this to calculate my theoretical yield. Well, theoretical yield in grams, I already have the moles of product, so I have one more step. I know which one I have to use. My last step is going to be 0.103 moles of zinc oxide. What relates moles to grams is the molar mass. Now I put moles of zinc oxide on the bottom because I want that to cancel, so I'm left with grams. And for moles of zinc oxide, I get 81.39 grams zinc oxide. The moles of zinc oxide cancel. Again, I'm using that limiting reactant that I figured out, and after I do this calculation, I should only have 3 sig figs. 8.38 grams of zinc oxide. Please use units throughout all of your calculations and watch your sig figs. I will be marking down for those that are wrong. Alright, cool. We got our grams of product. This is our theoretical yield based on the limiting reagent. Part B said, let's say you only recover 6.75 grams of zinc oxide. So what's your percent yield? So this is going to be your experimental over theoretical, and all of that times 100 gives your percent yield. The experimental is 6.75 grams of zinc oxide. We just calculated the theoretical yield in part A. So that's 8.38 grams of zinc oxide. Units cancel because percents don't have units. Multiply that by 100 and I should be at 3 sig figs still, 80.5%. It's pretty good yield. Question 2 was asking you, given percent by mass of elements, find empirical, then find molecular formulas. This is, again, chapter 9. You can look in the book or look at lecture notes. This is page 17 of the lecture notes. I outline the steps, so refer back to those when you're doing these questions. The first step is assume 100 grams because it's easy to convert percents into grams if you just have 100 grams. I'll show you a calculation if you don't believe me, but you basically can just take the percents and turn it into grams. Because it's 100 grams. If you're ever given a different amount of the compound, you cannot just convert percent to grams. You have to do this math if you're given something other than 100 grams of the compound. But for this class, you can assume 100 grams of compound for these problems. So it'd be this percent is equal to some number over 100 grams of the compound that we're assuming times 100, and we're solving for x. If I divide by 100 on both sides, that takes away the percent. How many grams out of 100 gives me this decimal? Well, I multiply by 100 on both sides, and that's gonna give me 89.09 grams. This is grams of Cl. Cl. For carbon, I have 10.06%, would become 10.06 grams of carbon. For hydrogen, 0.84%, please write the zeros in front of the decimals, becomes 0.84 grams carbon. This is much easier to read than this, especially if you're writing a lot. Sometimes I can mistake these for periods, or don't know if you meant to write it. Please write the 0.84. Alright, step 1, convert, assume 100 grams, and we're doing percent to gram conversion. Step 2, I'm going to do it on this page, so continuation of number 2. Step 2 is convert grams to moles of the atoms. So for carbon, we have 89.09 grams of carbon. Grams are related to moles by the molar mass. I just look at the periodic table. I'm just dealing with elemental carbon. So I want, that's chlorine, Cl. Be careful of your units as well. So grams of chlorine, if I look at the periodic table, I see that that's 35.455 grams of chlorine for every mole of chlorine. For carbon, we've got 10.06 grams of carbon. The molar mass is 12.011 grams of carbon for every mole of carbon. I want grams on the bottom so they can cancel, and I'm left with moles. And then for hydrogen, 0.84 grams of hydrogen. Molar mass of hydrogen is 1.00794 grams of hydrogen for every mole of hydrogen. Grams are canceling, the grams of carbon are canceling. Now I can put this into my calculator, and I end up with 2.513. Lowest number of sig figs is 4 here. 513 moles Cl. Lowest number of sig figs is 4 for carbon as well. So that's 0, that doesn't count. 8, 3, 7, 6 moles of carbon. And then the lowest number of sig figs for hydrogen is 2 from the given grams. So I get 0.83 moles of hydrogen. Alright, finish with step 2. Step 3, I now have the moles of each thing. I can put them into the empirical formula, and now I just need to work to make whole numbers out of these. So step 3, for chlorine, I have 2.513. Carbon, I have 0.8376. And hydrogen, I have 0.83. We don't have decimals of hydrogen. We either have a hydrogen or we don't have a hydrogen atom. So to make these whole numbers, because I can't chop up a hydrogen, I'm going to divide by the smallest number. Smallest is 0.83 in this set. That gives me 3.0, because again, I'm dividing, so I need to watch sig figs. It's 2 sig figs for each of these now. So 3.0, I just want to keep the 0.0 for right now just to make sure I don't have to round anymore. For carbon, it's 1.0 if I'm following sig figs. Oh, geez, chlorine, getting ahead of myself. Chlorine's 3.0. 3.0. Carbon, 1.0 for sig figs, straight up 1 for hydrogen. So we don't write the 0.0s here, but I'm keeping them here just to make sure I don't have to go on to step 4, which is multiplying by whole numbers until I can round. But here, we're good. We're within 0.1 of the whole number. They're already whole numbers. So my actual empirical formula would look something like this. You don't have to write the ones subscripts. You can if you want to, but it would be 3 chlorines for every 1 carbon for every 1 hydrogen. So this is the empirical. The molecular formula. So the empirical formula is the lowest common denominator version of this grouping of atoms of elements in this form. So molecular formula could straight up just be this, or it could be Cl6 carbon 2 hydrogen 2 if everything was doubled. You could triple everything, you could quadruple everything. The way you figure out what you multiply the subscripts by to get the molecular formula, well, here I give you the molar mass of the compound for the molecular formula. So the molar mass of the molecular formula to get the ratio of molecular formula to empirical formula, I can divide their molar masses. I have the molar mass right here of, I can figure out the molar mass of this from the periodic table. Chlorine, if you do the math, molar mass of chlorine times 3 plus the molar mass of carbon plus the molar mass of hydrogen, you will actually find it has the same exact molar mass as what is given. So that goes down here. This won't always be the case. You might find that your molar mass is larger of your molecular formula compared to your empirical formula. It can only ever be larger. That'll give me 1. Let me write this in a different color. So molecular formula, you're given the molar mass of the molecular formula. If I divide it, I get the factor that I have to multiply by. So now I'm going to multiply by 1. Seems silly, but I'm showing you this step because this isn't always going to be 1. So it also happens that the molecular formula is the same as the empirical formula, which is fine. So make sure you box and label your answers, and you are done with this problem. Question 3 is going backwards from what we just did. I want you to tell me the mass percents given a formula. This is on page 21 of chapter 9 notes if you want to watch that on the video again. For this question, there are steps as well, guidelines. Here, we're going to assume 1 mole of H2O2. And I need to determine grams of each element. This is a moles to grams. The subscripts always tell you moles. So if I assume I have 1 mole of this, I am saying 1 mole H2O2 So again, I'll show you one, but because we're assuming 1 mole, you can just take these subscripts. But what I'm saying is 1 mole of H2O2 over 1 mole H2O2. So for every mole of H2O2, I have 2 moles of hydrogen by itself. 2 hydrogens to make up 1 mole of H2O2, a single molecule. So I need 2 hydrogens. The moles cancel. Tells me I have 2 moles of H. To get from moles to grams, molar mass again, always and forever. Moles of H have to go on the bottom because I do not want them there anymore. Grams have to go on the top. I get this from the periodic table. I can do the same setup for oxygen. If I look at the subscript, I'm assuming 1 mole of that molecule. That tells me I have 2 moles of oxygen by itself. Not O2, just straight up 1 oxygen atom. It'd be a similar calculation here, but instead of 2 moles of H, it'd be 2 moles of oxygen. And then moles to grams, is that molar mass. Molar mass of oxygen, 15.9994 grams O2. Moles are canceling, and now I can calculate. That should be O. The molar masses, so multiply each thing by 2. I'm going to go out to the same number of sig figs because they're the only measured thing. And 2 times 15.9994 gives me 31.9988 grams of oxygen. Step 2, I determine the mass of the entire compound. So I'm just gonna add up the grams. So well, I have 2.01588 grams of hydrogen. Plus 31.9988 grams of oxygen. When you're doing these problems, you don't have to write out each step. It is helpful if you don't know where to start or get confused, but if you set these up figure out the grams, you could just add these together with your calculator. You don't have to write this out right here every single time. All right, what is my least certain? 1, 2, 3, 4, 5. Goes out to the 5th. 1, 2, 3, 4. This one. So I can only go out to the 4th decimal place because I'm adding. There's 1, there's 2nd decimal place, 3rd, and 4th. Grams. Molar mass of this. Done. All right, cool. Now, I just determine the percentages of each element. So, how much of H2O2 is hydrogen by mass? How much is oxygen by mass? I'm going to take the two numbers I got here and divide them each by the total mass. Multiply them by 100, and I have the mass percents. Let's do that. So now we're on step 3. So for step 3, we are gonna take percent of hydrogen. Well, my mass of hydrogen is this, and I want to know how much of this makes up the total mass. So I need to take it and divide it by the total mass. And I multiply this whole thing by 100. Least number of sig figs, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They're the same, but doesn't matter here. So this right here, when you're doing mass percents and you get to the percent part, round percents to hundredths place. Just for these types of problems only. So I get, for hydrogen, 5.9. I stop at the hundredths place. So this is going to be, I'm going to round. So I get 926, blah, blah, blah. But I round to 5.93% H. For percent O, I am going to take this, and I am going to divide it by the total mass. How much of the molecule is made up of oxygen by mass? Multiply that by 100 again. And I get 94.073 other things, but I'm rounding to the hundredths, 0.07% oxygen. This is step 3. Step 4, add check yourself. Add percents together. They should be close to 100. 94.07 plus 5.93. 100%. And you're done. So these are the percents by mass. 94% of H2O2 is oxygen. 5.93% of H2O2 is made up of hydrogens.